So, let us resume our discussion of kinetic dynamos. Kinetic dynamos, as we said earlier, are ones where the velocity field is prescribed is given to us and through some other means, okay, and we look at the evolution of the magnetic field, evolution of B via the induction equation, okay, induction equation which we have seen many times. dB dt is equal to the curl of V cross B, right, plus possibly a resistive term, and we will talk about that in a minute, right. So, now the two things about any dynamo: you should show that the presence of a small seed magnetic field renders the system of equations unstable, so that the seed fields grow, because we are interested in knowing the origin of large scale relatively stable magnetic fields. That is really the problem of a dynamo. Okay. So, there are two things in a dynamo. Number one is to show that the presence of a small seed magnetic field renders the system of equations unstable, making the seed field grow into a large scale magnetic field. That is point number one. Point number two is to show that the fields, having grown to appropriate values, can sustain against that decay, because that it's not as if there is always a resistive term here. There is no matter what you do, there is always a resistive term, this kind of a resistive term, with where the lambda is related to the conductivity. All this is in CGS, mind you. So, C, okay, where this is the conductivity. So, this resistive term might well be small, but it is there, okay. And remember, so in the face of resistive decay, the dynamo has to somehow keep regenerating the fields, so that the fields do not just die away, okay. And it turns out that this is a non-trivial problem, okay. The second term, this term, it contributes to the decay of magnetic flux, and so it turns out that the decay problem is not such a simple problem, is not such a trivial problem. The first term in this equation is order is of the order of VB over L. This is the first term, and the second term is of order lambda B over L square, second term. And as we know, the ratio of these two terms is the Reynolds number, right. Now, it turns out that if you calculate the time scale of decay, okay, the time scale of decay by considering only this term and this term, okay, with this term not being there, this gives you the time scale of decay. Just look at this and this, okay. You can figure that out only from the length scale and the conductivity. You can figure that out just from this, okay. So, let's look at the time scale of decay for certain well known objects. For the Earth, it turns out that the decay time scale is something like 3 times 10 raised to 5 years, the resistive decay time scale. Given the values of the conductivity and the length scales and everything, the time scale for resistive decay for the Earth is something like 3 times 10 raised to 5 years. For the Sun, it is something like 10 raised to 11 years if you put in the appropriate numbers. Okay. And for the galaxy, for our Milky Way galaxy, it's something like 10 raised to 23 years, really huge. Now, this is really large, so as such there really should not be a problem, but it turns out, at least for the Sun, okay, Sun has been around for considerably more than this, and so you do need a dynamo. So as such the field would have decayed away, okay, before this, and so but you do need a dynamo to regenerate the field, and at least for the Sun it becomes a bit of an issue because we've seen that there's observational evidence that the field is not only regenerated, but it also flips every 11 years. Okay, so these are the challenges kinetic dynamo theory should address, or rather the version of the kinetic dynamo that we will be adopting addresses mostly the second question, which is how does the field retain its identity in the face of resistive decay. Okay. Now, the main thing to remember is the frozen in condition, which we discussed at length a little while ago, the frozen in condition for B fields. In other words, the fact that whatever the velocity field does, the B field obeys. Okay. So, this is one of the main things to remember. In other words, the velocity field drags the B field with it. This is the essence of the frozen in condition. Okay. So, one tries to see what follows. We will discuss the magnetic field of the Sun. Turns out that we have a little more of a basis for understanding the basis how the magnetic field on the Sun is generated than for the Earth itself, simply because we have more regular observations. So, it's a bit ironic, but it's true. Not to imply that everything is known about how the solar dynamo works. No, not at all. There are big gaps in our understanding. But one thing I would like to make clear, there is no, you see, the point is the solar plasma, through plenty of observations, things like the temperature, the conductivity, and the time scales over which things vary in the solar plasma. These things very well. Okay, and especially with regard to the time scales. In other words, we are mostly interested in low frequency phenomenon. Okay, and so there is very solid ground to believe that really whatever phenomenon controls the solar magnetic field is governed by the magnetohydrodynamic equations. Okay, in other words, the basic assumptions that go into magnetohydrodynamics are well satisfied for any mechanism that is supposed to be generating the magnetic field on the Sun. And if that is so, we know that one of the central cornerstones of magnetohydrodynamics is that the only current there is a displacement current. Okay, in other words, J, the current density, is simply the curl of B. Okay, there is no other physical current being driven by batteries or anything, because at these scales the plasma is essentially neutral. Okay, there is no reason to believe that this neutrality is destroyed. Okay, and even in the solar wind, even out in the solar wind, outside of the solar atmosphere, where near the Earth, we have detailed observations of the solar wind plasma, and there is really no reason to believe that the large scale neutrality is in any way destroyed. So there is no net current anywhere. Okay, and so it is, if one sort of thinks that that there is some kind of a net current that gives rise to a magnetic field from Ampere's law, that is not true. Simply because there is no scope for a net current. Okay, so one has to look for alternative ways of how to generate the magnetic field. It's simply not, certainly not via any kind of a net current. That is simply not present in MHD, and the conditions appropriate for MHD are amply satisfied both in the solar interior and the atmosphere, and farther out in the solar wind. Okay. So, which is why we have to resort to slightly more complicated pictures like the kinetic dynamo, which is successful in explaining, I would say, 60–70% of the solar magnetic field puzzle, but not all. Okay. So, let us see how much we understand. Okay. So, the frozen-in condition essentially says that the velocity field drags the B field with it, and so let us try to see, given this, what components of the magnetic field can be generated and how the overall magnetic field is sustained. Okay. So, right now, as it happens, there is something called an anti-dynamo theorem, and I am not going to elaborate on what this is. You can Google it. What it says, it's called the Cowling's anti-dynamo theorem. Which says that an axisymmetric field, an axisymmetric velocity field generating an axisymmetric magnetic field is not permissible, hence the name anti-dynamo. Okay. And I am not going to go into exactly what the Cowling's anti-dynamo theorem is. So this would be a very simple situation where you come up with, this would be the simplest of explanations. Unfortunately, the simplest of explanations is not permissible. What can one do? Okay. So let us look at a kind of a pictorial idea of how solar dynamo might possibly work. So let us draw a cartoon of the sun like so. Sorry, this is a terrible, anyhow, I mean, so something like this. Okay, and let me erase this. I don't know why this is not working. Right. Okay. Now, so that would be the surface of the sun. One of the main things about solar observations is that it's been observed from surface observations. Now, what we are talking about is magnetic field generation in the interior of the sun, not on the surface. Let's keep that firmly in mind. But nonetheless, we have to make do with only surface observations. But from surface observations, it's now spanning nearly 100 years. It's evident that the equator rotates faster than the poles. Okay, so this is called differential rotation. Okay, the equator, and you might wonder, rotates faster than the poles, like so. So this would be a sketch of the velocity of the phi directed velocity vector at the equator, and that would be a sketch of the phi directed velocity field near the pole. So this is longer than that. Okay. So this is one of the main observational pieces. Now what does this do for us? Okay, what this does for us is the following. So again, let me try to draw a circle like that. Okay, imagine an initially, now you always have to start with a seed field. Imagine an initially z-directed magnetic field. Yeah, now the equator, this part is rotating faster than this part. So what will happen is this field will kind of get distorted into something like this. So, this is what it used to be. Okay, it used to be from bottom to top, but because the central part is moving faster than the top part, what is happening is the central part is getting dragged out more as compared to the top part. Okay, and this is why is it getting dragged out? Because the magnetic field is frozen into the flow. Okay, and now this entire thing, remember, this is not happening at the surface, it is happening well beneath the surface. Okay, so you started out with a z directed field, start with z, and you produce from dragging of the field due to the fact that the field is frozen into the velocity flow, which exhibits this differential rotation. It enables us to produce an azimuthal component. You can see that an azimuthal component is present in it. This is no longer a purely z directed field. It is a z directed field plus a phi directed field. Produce phi hat, a phi hat component. Start only with the z hat component and you produce a phi hat component, you see. So, this is one thing. Now, but this is not all, right. The point of the whole dynamo, if the dynamo should work, then we should find some way of reinforcing this z hat component. You started out with a seed field and somehow the dynamo needs to go back and strengthen the z field so that it can remain strong in the face of resistive decay. So, this is our main thing. Now, it turns out that there is one more issue here, one more important component, and that is a little, shall we say that stretching things a bit. If this was not there, the whole thing would not work, and that is called the issue of helical turbulence. And let me try to explain what this is in a minute. Turns out that the interior of the sun, if I remember correctly, the last 30% of the sun's depth, okay, it is convectively unstable. Okay. What this means is that there are always convective bubbles in the plasma which are flowing. Okay. So, these convective bubbles, you see, so you have to accept the fact that there are convective motions, convective rolls, okay, so convective rolling motion in the interior. This is one important part, okay, and these convective motions are subject to Coriolis forces. These convective cells are subject to Coriolis forces. Why? Because they are in a rotating frame of reference. Okay. And the Coriolis forces are of opposite directions in the two hemispheres, in the southern and the northern hemisphere. You see, if you are standing on the north pole, you have your head pointing this way, whereas if you are standing on the south pole, you have your head pointing this way. Whereas the rotation of the sun is in the same direction. It might be differential, but it is in the same direction. So, the handedness is different. The handedness of the rotation for the person whose head is pointing this way is different from the person whose head is pointing this way. So, the handedness of the Coriolis forces are different in the northern hemisphere and the southern hemisphere. So, the handedness of the Coriolis forces are different in N and S hemispheres. Okay, so and therefore what's going to happen is this guy is going to get distorted by the fact that there is little inside the plane of the paper. There are these convective rolling motions, and I'll try to sketch it. So, let me first sketch these guys and let me first sketch these guys, if you remember, this is pointing this way and this is pointing this way. This is exactly the same as this, exactly, except what's happening in between I have not yet done, and I'll do it in a minute, right. So what's going to happen here is that this guy is going to get modified like this, get connected here, and this guy is going to get modified like this and get connected here. It looks like this, and this also looks like this. Okay, so this thing is simply connected like this, and this thing is simply connected like this. Okay, remember these rolls are in a plane perpendicular to the plane of the screen, in the meridional plane. Okay, this is very important to realize. Okay, and the handedness, you see this guy is pointing this way and the rolls are this way, and this guy on the other hand is pointing, so this would be the north hemisphere and this would be the south hemisphere, and this is the equator. This is the equator. Okay, so the handedness in the northern hemisphere and the southern hemisphere are opposite. Handedness in north and south hemispheres are opposite. You point your thumb this way and do a right hand rule, and here you point your thumb along the direction of the field and you do a right hand rule. You'll find that the sense of rotation is opposite in the northern and the southern hemisphere. That arises from the fact that the Coriolis forces are in opposite directions in the northern and the southern hemisphere. Okay, because the direction of rotation is the same. Okay, the phi direction is the same, but in the northern hemisphere, a person standing on the north pole, for instance, has their head pointing this way, and on the south pole, on the other hand, they have their head pointing in the opposite direction, like that. Okay, so that's that person's head out there. Okay, so the handedness are different. Now what happens? So these rolls are in the plane, in the meridional plane that is perpendicular to the plane of the screen. So let us now try to look at the meridional plane, and let me draw the thing again, like, and in the meridional plane like this, what I have is several little rolls like this. Okay, and the sense of the roll is like this, yeah. Like this, yeah, and all the rolls are like that. These are little convective cells deep inside the solar atmosphere, and what happens is these convective cells, these little cells, which are each of these guys, fuse due to diffusion. In other words, what will happen is the boundary between this cell and that cell kind of merges, they fuse. Okay. Now let us look at what is the general direction in all along this boundary. The general direction of the field is like this. Okay, so this is an arrow pointing this way, and what is the general direction of the field here? It is like this. An arrow pointing this way, yeah, and the general direction of the field is like this here. An arrow pointing this way. Okay, so what's the magic that's happened now? Two things are very crucial here. One is that so this arrow is pointing this way, this arrow is pointing downwards, and so on and so forth. Okay, and so this would be at the very surface. Okay, this is well in the interior, and this is well at the surface. This is a cross section. This is a cross section that is that is perpendicular to the plane. So, it is that cross section that we are showing here. Okay. So, this would be at the surface, so to speak, at the surface. So, what is going on here? What is going on is that, so there are two things, just to remember, there are two things that are crucial. One is that the handedness should be correct. In other words, the helical turbulence should have the proper handedness, and that is reasonable to expect, but that is still somewhat contrived. I'll admit to it. And these little cells will have to fuse due to diffusion, so that the overall, when you add up these little cells on the periphery, the field looks like this. And on the periphery, what is happening? The large scale field is pointing from the bottom to the top, and that is exactly what we started out with. You see, the large scale field was pointing from the bottom to the top. Okay. So, the large scale field is again z directed. So, it reinforces the original field. It reinforces the field that we started with. We started out with a large scale z directed field. We generated a phi component, and from the phi component we twisted the phi component appropriately in a certain manner, and we let these little convective cells fuse, and in fusing they produce a large scale field which adds to the original large scale field. It reinforces the original large scale field, and so our cycle is kind of complete now. All right. So, this is a very brief sketch of how the solar dynamo, of how this is a very, not so much the solar dynamo, it is a very brief sketch of what is called the alpha omega dynamo. The omega refers to the differential rotation, because omega is generally, and the alpha refers to this kind of this helical turbulence, so to speak. And there are several things. There is a very brief sketch of the alpha omega dynamo. It does not address, at least the way we have sketched it, it does not address the solar cycle, 11-year change in the magnetic field. This is just a very basic, that's all. The only reason I said this, I brought this up in the context of this course, is that it relies crucially, this whole thing, you see, this whole sketch, this guy, the fact that the z directed, the initially z directed field is dragged and to produce a phi component, and the fact that these convective rolls, okay, what are the convective rolls? Convective rolls are essentially velocity fields, that is what they are, and the velocity fields also drag the magnetic fields to form little loops in very specific directions, okay, and then the little loops fuse together and so on and so forth. But all of this, the entire phenomena is very crucially dependent on the velocity field dragging the magnetic field. It is very crucially dependent on that. Okay, and what is this a consequence of? This is a consequence of the induction equation. And the induction equation is something that we have spent a fair amount of time on. So, I just wanted to end this section by illustrating how the centrality of the induction equation, and how one of the key predictions of the induction equation results in explaining at least in giving at least a very skeletal overview kind of sketch of the alpha omega dynamo. Right? Okay. So, that is all we have time for right now, and we will get into a completely different topic the next time we meet. Thank you.